All right, so today we're going to be looking at more applications of Ka. That is the acid ionization constant. This, of course, is in Chemistry 30. Uh, it's not in the title of today, but we're also going to be looking at the base ionization constant as well. You're going to find it's very, very similar to finding Ka as well. Anyway, let's get started. So today's plan, it says we'll start by going over the questions from last class. We're not actually going to do that today. I'll go over that when I'm back in person, of course. But what we're really going to do is we're going to look at different examples involving calculating Ka, again, the acid ionization constant today. And like I said, also we're going to look at calculating Kb, which is the base ionization constant, very, very similar to Ka. You should actually have a decent amount of time to practice this today, although some of the questions that I'm going to throw your way during our actual lesson today are kind of curveball ones, especially our KB one, just because we have to spice things up a bit when we're, doing something that's almost the exact same thing as what we've been doing. Not a huge amount of new information today, though, but let's get started. Here we go. So these are the questions from last class. We're just going to skip that for today. We're going to just move right on to this new one. The pH of a 1.00 mole per liter solution of acetic acid is carefully measured to be 2.38 at SATP. What is the value of Ka for acetic acid? So before we do this question, first of all, you might be wondering, and I may have addressed this in class already, but you might be wondering in you know, your data booklet for chemistry 20 and 30, which you're allowed to take into every test and even the diploma exam, of course. Well, you get a fresh one for that, but you know what I mean. In that data booklet, though, on page 8 and 9, there's your list of acids and bases. And on the far right column, it does have a column for Ka values. So you might be wondering on a question like this, can't we just look up acetic acid in that chart and then say what the Ka value is? And the answer to that is yeah, you could, but because the question is giving us an actual experiment that we're dealing with here, it's just proper use of this to actually calculate given the information we've got. And I know how much longer that takes, but the answer you get experimentally could be a little bit different than the answer that actually appears in your data booklet. That's why it's important to check. I really appreciate it when questions actually tell you to like, oh, use your experimental data to find this, but it is what it is. Anyway, long story short, we have to do this the longhand way. So before we begin on this one, just a reminder that we have a before and an after. We have an initial as well as equilibrium that we're dealing with here. Initially, we know our concentration of acetic acid, and we know its pH. The pH is basically going to be what it hit at equilibrium. So we can use that pH to kind of figure out our equilibrium pieces. Because we're dealing with an equilibrium reaction here, we have to come up with an equilibrium reaction equation to show us what's going on. Acetic acid, if you don't know what that is, you can look at it on your acid base chart. Acetic acid is CH3COOH, so I'll start by writing that down. CH3COOH. And because we're talking about its pH, we need to figure out something about its hydrogen ion concentration or hydronium ion concentration. And to dig that out of there, we'll draw the equilibrium reaction by adding H2O, doing our double-sided arrow for equilibrium. And of course, since this is an acid, it's going to produce H3O positive. That's our hydronium, and of course we can use that with our pH. Plus, of course, in order to bump H2O up to an H3O positive, it must have gained an H somewhere. Well, it would have taken an H off that CH3COOH. So I'm going to write this now as CH3COO, and since it lost an H, it now has a negative charge. Also, just because it's really important for dealing with an initial and an equilibrium for calculating our Ka value, it's just good habit to get into writing your states on all these things. Acids, of course, are going to be aqueous. H2O would be liquid. H3O is going to be aqueous, and then same with this other product will be aqueous because they're ions. Anyway, again, as I was rambling about a second ago, because this is our initial amount, we should set up an ice chart to help us organize this. So just to remember, an ice chart is a useful way of organizing the concentrations of your initial and then your equilibrium entities in your reaction. So if I'm going to make my ice chart, remember we set this up by just drawing our chart here. Ice is going to be initial, change, and equilibrium. List out your entities that actually matter in terms of calculating Ka. Remember, they all have to be the same state. Solids and liquids can be ignored, so that means our water can be totally ignored here. So my entities are going to be CH3COOH, and then H3O positive, and then CH3COO negative. And I'll just make this chart a little wider. And there we go. It's kind of hard drawing this because my pen tablet, it's just like a tablet on my desk and I can't see where I'm writing until I look at the screen. It is what it is. Anyway, so the only thing that I know here in terms of initial right now is my acetic acid. So I'm going to say that that's 1.00, and again, everything in an ice chart always has to be measured in moles per liter. So I'm not going to bother writing the units on that. You can if you want to, but ice charts are always moles per liter anyway. Now, it doesn't tell us anything about this already having H3O positive or CH3COO negative before we started doing this. So it is a safe assumption in this case because we don't know anything about the initial. It's a safe assumption just to say that those are zero here. Not only is it a safe assumption, it's a matter of fact because what we're doing in this is we are ionizing this. We're actually putting acetic acid in solution and measuring the pH from it, which tells us that we are ionizing this into H3O positive. We're producing those kind of ions. Now the next row I always find is the easiest one. If you have your balanced equilibrium reaction, this next row is very simple. It's your change row. Remember, your reactants are always being subtracted. Your products are always being added. You use the coefficients in front of those things to determine how much you're adding or subtracting. Long story short, for CH3COOH, because that is a reactant, it is going to be minus. And because there's only a 1 in front of it, it's minus 1x. For H3O positive, since that is a product, it's going to be plus. And since there's a 1 in front of it, it's going to be 1x. And the same with this guy over here, because it's a product, it's going to be plus. There's a 1 in front of it, so it's 1x. Now, as for equilibrium conditions, we're kind of hooped for a second here, right? We don't have any equilibrium moles per liters that were given to us. The best thing that we have is the pH of 2.38. Now, I need to stress the importance here. It's very important to understand that there is a formula that links pH to your H3O positive concentration. And the unfortunate thing is this formula is not provided to you. You just need to remember it. The formula that connects them is the H3O positive concentration is equal to 10 to the negative pH. That's a formula that you're just going to have to start burning into your mind. With enough practice, this kind of becomes second nature. It just is what it is, right? Anyway, so to find that H3O positive concentration, we can just go 10 to the negative 2.38. Give me a second. I'm just going to type this in my calculator. 10 to the negative 2.38 gives me a pretty gross decimal. I'm getting 0.00416, and then I'm going to round that to 69, we'll say, right? It's enough significant digits in there for it not to really make a huge difference. Anyway, that's our concentration of H3O positive. And because that H3O positive was produced after we added the water, it's safe to say that that concentration is going to be our equilibrium. So I'm going to write that number right in here, 0.004169. Now notice we now have a vertical column finished. And when you have a vertical column finished on an ice chart, that's actually kind of the holy grail of the whole thing. You now have a formula that you can work with. The formula is always the initial, then your change, then your equilibrium. So how this one is reading is 0 plus 1x becomes this number here. Well, 0 plus anything just is that anything, right? So the 0 is not doing anything here. So really it's just saying plus 1x equals this number, which of course just means x is that number. What that means is this other column here, the CH3COO negative, we can actually now finish this because we know x is just this number. So 0 plus this number is once again this number right here, 0.004169, right? So that's another piece of our ice chart that we were just able to figure out from there. The real question is, though, how do we finish this last one? Well, it's the exact same thing. We just need to take our initial of 1 and then minus that 1x. So minus 0.004169. I'm just doing this with my calculator in person here. Anyway, what I got was 0.995831. That's going to be my equilibrium concentration of CH3COOH. Now, why was this so important to fill out the ice chart? I don't think I actually properly explained that. Sorry, guys, if I kind of just was rambling there. It was a before and after, so I was kind of just set in my ways. The whole goal here is we're trying to find Ka. And just like any other equilibrium constant value, like we used to find Kc when we were first learning about equilibrium constants. Ka is no different. It's just the acid ionization constant for this whole thing. Ka can be found by taking the product of all of your products concentrations divided by the product of all of your reactants concentrations. But remember, we don't count solids or liquids. We only count everything that's aqueous, if everything was that case. In more simple English, I guess, or written out in a way that's a little more understandable, it's going to be our products. So it'd be H3O positive, more correctly, that's its concentration, hence why I'm using the square brackets, multiplied by the concentration of CH3COO negative. We don't have to square or cube any of these because notice there's no coefficients in front of them. The coefficients are just 1. If there was a 3 in front of this thing, we'd have to cube that. Just remember that from before. Divided by our reactants, but remember we're not going to include water because it's a liquid, so it's just the concentration of CH3COOH. And remember all these concentrations, because this is at equilibrium, must be our equilibrium concentrations. So it's these guys just down here. We're now ready to plug all this in, finally, right? So Ka equals H3O positive, well, that'd be 0.004169 times CH3COO negative is, once again, 0.004169. If you wanted to save yourself some trouble, because if you knew those numbers were multiplied together and they're the same thing, you could have just squared one of them. That's all the same. Anyway, divide that by 0.995831. So give me just 2 seconds here. I'm going to throw this in my calculator. Taking that number divided by that number. Anyway, long story short, we got to watch our sig digs because this is finally my Ka value. The number of sig digs in this question to the untrained eye looks like 3, but remember pHs are really weird. For pHs, only the numbers after the decimal count is sig digs, and zeros there would count too. Not that there's any zeros there, I'm just letting you know. Long story short, there's only 2 sig digs here. Right? So there's only 2 sig digs in this, so my answer only has to have 2 sig digs. My answer is actually going to round to 1.7 times 10 to the negative 5. And these equilibrium constant kind of things, or acid ionization constant in this case, they don't actually have any units. They're just a number, right? They're just a constant. So 1.7 times 10 to the negative 5. And if you were to look on your data booklet, the answer that it has on there is actually 1.8 times 10 to the negative 5. So when I started this question, I said, hey, why can't we just use our data booklet and figure it out? Well, it's because they gave us experimental data. We have to work with that, right? It's pretty darn close, but we still got to work with it. It is what it is, okay? So anyway, that's how we find Ka just from scratch. Because they gave us initial stuff here, we have to use an ice chart. It is what it is, right? Ka is all about equilibrium. In order to jump from equilibrium or from initial to equilibrium, you got to use an ice chart. It is what it is, right? Your turn. Mwahaha, right? So this question, very similar to the one we just did, but you need to make sure you're getting essential practice of this. I really encourage you to work with a partner if need be. Pause the video here. Give this one a try. It should take quite a few minutes. Give it a shot. All right, I'm going to go over this one. I'm going to kind of speed through this one just for the sake of time. This time around, we're dealing with sulfurous acid, right? You need to check your acid chart just to see what on earth the formula for that is. The formula for sulfurous acid is H2SO3. So we'll start with that first, H2SO3. We're given its pH, which is kind of our hint that we need to ionize this to pull out H3O positive, because that's the link between pH and concentration. So I'm going to add water to this. Realize that it is an equilibrium reaction, so a double-sided arrow. This is going to produce H3O positive plus HSO3 negative. So the H2SO3 donated one of its H's to the H2O to bump it up to H3O positive. And of course, the states, just for good measure, that's aqueous, liquid, aqueous, and aqueous. Okay, now I'm going to set up my ice table, because this is an initial concentration, right? So if I'm going to set up my ice table, just bear with me here. Here we go. It's not the smoothest looking thing, as you can see, but you know what? I'm just doing this for the sake of time. H2SO3, H3O positive, and HSO3 negative. Forgot to mention, by the way, I'm actually really appreciative with the wording of this question, because they did say calculate the Ka from this evidence. I wish they would all write that. Can't even argue it on this one. We got to use the actual calculation here. Anyway, fill out our ice table here. The only thing that we were given right off the bat was the pH of the sulfurous acid, so 0.400. We can assume that these are both 0 because, of course, we are ionizing this. We wouldn't have those in the first place. Do the whole change thing. If you look at the coefficients here are all 1. So this guy's going to be minus 1x. This one will be plus 1x because it's a product, and this one will be plus 1x because it's a product. Then we can now figure out one of our equilibrium stuff by using our pH. Remember, the formula is H3O positive concentration is 10 to the negative pH. So in this case, that's 10 to the negative 1.17. And I am pretty sure that that gives us 0.067608. That's our concentration at equilibrium of H3O positive. So let me throw that in here, 0.067608. Notice now we have a vertical column. That's a holy grail of an ice chart. You have a vertical column, you got everything. You're all set. You can find that x. 0 plus 1x equals this. Well, then that just means that plus 1x is that number, which tells us for HSO3 negative, it's also that number. Ooh, there we go. That's better. 0.067608. It's also that number there. Since we now know what x is, we can also finish up this other column, 0.40 minus that 1x, that 0.067608. Long story short, you're going to get 0.332392. So that's that guy's equilibrium concentration. Our formula for Ka in this case is our products over our reactants. So that's going to be our H3O positive concentration times by our HSO3 negative concentration divided by our H2SO3 concentration. Notice we're leaving out water because it is a liquid. It is not technically the same state as those other things. Anyway, let's throw these things in. If you throw these things in, we got our 0.067608 multiplied by another 0.067608 divided by the H2SO3, which is 0.332392. Very tedious writing all those numbers in there, but it is what it is. Anyway, my final answer to just 2 sig digs, because look, once again, we got that pH throwing us off. We only use the number of digits after the decimal when we're given a pH. So 2 sig digs in this question. I'm getting 1.4 times 10 to the negative 2. And again, there are no units on a K value. It's just a constant. So hopefully that one went well for you. Again, these are very tedious. They do take quite a bit of time, but that's just how it goes. So our new thing today, base ionization constant. You're going to see that this is pretty much the exact same thing as acid ionization constant, except when we do our ionization reaction for a base, remember, we're not producing H3O positive, we're producing OH negative. That's the telltale sign that we have a base, right? So examine the following generic equation for a weak base reaction. We have B, whatever that is, just some aqueous mixture, plus H2O liquid, and that's going to create HB positive. So in other words, that B gained an H, and therefore its charge went up to a positive 1, plus OH negative, right? So that H2O donated its H to the B, and there was an OH negative left over. So unsurprisingly, the aqueous B in this case is representing our base. Now, could we create a Kc expression for this equation? Well, of course we could, right? We need to just watch our same states. So Kc equals, that would be our Hb plus multiplied by our OH negative divided by our concentration for B. We're not going to include water because it is a liquid. It does not match the other ones. But this is so significant, this whole thing for Kc, that in chemistry, because we're dealing with a base here, it's going to serve as the base ionization constant. So rather than calling it Kc, why don't we just knock that off and call it Kb? Pretty much the exact same thing. So if this feels like the exact same thing as what we've been doing for like a week, yeah, it kind of is. So as we're dealing with bases this time instead. And the reason that's useful is we can actually deal with this by giving like a pH or a pOH value. That's the real sneaky thing here. Remember, OH concentration does not come from pH. It doesn't come from pH at all. What it does come from is pOH. But the good news is the link between pH and pOH is the fact that these two things always add up to be 14. Or in other words, if you took 14 and subtracted one or the other, you'd get the other one. That is what it is. So that's one of the sneaky things about this. Anyway, let's see the one and only example that we're going to deal with today. Just a bit of a heads up. it's a bit of a long one, so bear with me on this one. So one of the uses for aniline, whatever that is, C6H5NH2, is in the manufacture of dyes. Aniline is soluble in water and acts as a weak base. When a solution containing 5.0 grams per liter, that's going to be a thorn in our side here, guys, just by the way, those are a horrible unit, of aniline was prepared, the pH was found to be 8.68. Calculate the base ionization constant for aniline. So I'm not going to scan through our acid base chart, but I feel like if I was someone who was willing to put a bet on this one, I feel like aniline is not going to show up on that acid base chart in our data booklet. So you couldn't even like look it up if you tried, right? I mean, you could Google it, but that's beside the point. Base ionization constant, we want to calculate this given the information we've got. I would say the first thing we should do is create an equalization reaction. Okay, let's get a formula going. So C6H5NH2 plus water, double-sided equalization or equilibrium reaction here. We are already told in the question that this thing is acting as a weak base. So we know automatically that OH negative is going to form. Since OH negative is going to form here, that means the H2O must have donated one of its H's to this other guy here. I don't know exactly what that's going to look like, but if I were to bet on this one, it's probably going to be C6H5N, and then instead of H2, we tack it on to be NH3 for whatever that is, right? Now, we're making a solution of this, so I think we can assume, oh, not even just an assumption, this thing gained a hydrogen. It must have a positive charge. My mistake, I almost missed that. I feel like we can make an assumption that this is going to be aqueous. Water, of course, is liquid, and then these two things are ions, so they've got to be aqueous. Anyway, what that leads us to is this leads us to making ourselves an ice table. I'm going to do that way over here where I got a little bit more room. We've got to make an ice table here because we have some before and after conditions. This thorn in our side is going to cause us some grief in just a second, but I'm going to show you how we can deal with that. We don't like grams per mole when we make an ice, we don't like grams per liter when we make an ice table. We like moles per liter. We'll talk about how we'll deal with that. Anyway, ice chart. ICE. We have our aniline, that's the C6H5NH2. Then we have our OH negative. And then we also have that horrible thing, C6H5NH3 positive, whatever that is, just some form of ion of that. Doesn't really matter. There's our ice table. Now here's where we kind of get a little bit hooped. When we go to make our ice table, like I said a second ago, you have to be using the units of moles per liter. These are all concentrations that go in here. We weren't given moles per liter here. We were given 5 grams per liter of this weird aniline stuff. The closest thing we can get to on this is, of course, we can do our change row because that just involves using our coefficients. C6H5NH2, our aniline, is a reactant, so it's going to be minus 1x because there's only a 1 in front of it. And then our two products also only have 1's in front of them, so it's plus 1x and plus 1x. In a way, compared to what we did like in the earlier part of this unit when we first learned about calculating the K value, those equilibrium reactions were almost a lot more difficult because they had those coefficients, and that changed what those C column or that C row look like, right? But anyway, I'm rambling here. The other thing we can calculate here is our pH can link to H3O positive concentration. But be careful. pH, again, like I said, goes to H3O positive concentration. We have OH negative concentration. Those don't go hand in hand. So here's my tip to you. pH is great for when you're finding your acid stuff. But when you're finding your base stuff, let's switch that to a POH. To switch that to a POH, we just need to go 14 minus 8.68, which equals 5.32. That is our POH. And the formula for finding our OH negative concentration is like a total mirror image of the one that we had for H3O positive. OH negative concentration is 10 to the negative POH. So let's throw this in. 10 to the negative 5.32 gives us, it's going to be a pretty gross number. I'm getting, I'll even leave it in scientific notation here, 4.7863 times 10 to the negative 6, running off the screen there, but you get the idea. Anyway, that is my equilibrium OH negative concentration. So I'm going to write that really small down here. 4.7863 times 10 to the negative 6. That is going to be this piece here. Now, I think I forgot to mention when I was making the size chart, is that just like before, we can assume both of these are zero because again, we didn't ionize this until after we added water. So why would we have these things in the first place, right? Anyway, that hopefully isn't a big concern. My point is we can now figure out our equilibrium amount for this other guy because we have a full column. We have that holy grail. So this has got to be 4.7863 times 10 to the negative 6. The real sticking issue here, though, still remains that we don't know our initial amount of that aniline. We were told it was 5.0 grams per liter. That's a thorn in our side because we want it to be moles per liter, not grams per liter. That kind of implies that we want to somehow figure out how we can switch our grams into moles. Think about that for a second. We want to switch grams into moles. Well, the only way we could ever switch grams to moles was using our molar mass. It's been a while since we've seen molar mass, but molar mass can be found just by taking a trip to your periodic table and adding up the molar masses of every element that make up that compound. Just for the sake of time, I'm going to save us some trouble on this one. If you want to show the work to the side, you can go for it. We're going to have 6 carbons plus 5 hydrogens plus 1 nitrogen plus 2 more hydrogens. I'm going to save you the trouble here because hopefully we all know how to find molar mass at this point. It's been something we did a million times back in Chem 20 and a bunch of times earlier in Chem 30. I'll save you the trouble though. The molar mass of this thing is 93.14 grams per mole. So 93.14 grams per mole. That's the molar mass of that aniline right there. Okay. Now, this still doesn't quite answer the question of how we get moles per liter. But take a look at your units. We have 5 grams per liter. So watch this, 5.0 grams per liter. We want to get rid of the grams and leave the liters down in the bottom. We have grams per mole right here in this 93.14. What if I flipped this number upside down? What I mean by that is what if I wrote it as 1 over 93.14 moles per gram? Oops, moles per gram. Moles per liter is what I just wrote. That's bad habit. Anyway, so 1 over 93.14 moles per gram. If I take these two numbers now and multiply them together, so 5.0 grams per liter times 1 over 93.14 moles per gram, notice that the grams on the top will cancel out with the grams on the bottom, and you're going to be left with units of moles over liters. Very sneaky kind of thing here. If you're not comfortable using that method, you could have just assumed in this question, because we don't know how many liters or how many moles we have, we could have assumed, especially by the balance equation, that you had 1 mole, and therefore you would have 93.14 grams, and then you could have like multiplied this, by 1 over 93.14 to get rid of the grams there. It's all the same thing either way. Long story short, if you throw this in, we're going to get 5 divided by 93.14. Give me a second here. Let me just calculate that. 5 divided by 93.14, which gives us 0.05368 moles per liter. And that's your initial concentration of that aniline. So I'm going to come back to my ice chart and fill that out. Told you this one was going to be kind of crazy, but that was the worst part of it. Anyway, let's fill out the rest of our ice chart now. We know our E value is this 4.7863 times 10 to the negative 6. So if we subtract that away from this, give me a second. If we go 0.05368 minus 4.7863 times 10 to the negative 6, hold on. A lot to type in a calculator. Here's what we get. We get 0.0536752. I'm just going to finish it right there. You know what? Actually, I'll write that a little smaller so it doesn't look as terrible. 52. There we go. Perfect. All right. Finally, home stretch. You know what? We should almost like pick a different color here to celebrate this thing. Does green work? Green's, it's all right. You know what? Maybe even a lighter. This one? Yeah, that one works a little bit better. Kind of a lime green. Anyway, let's finish this up here. We want to find our KB expression. After all this work, we're finally knocking on the door of it here. The KB expression here is going to be our two products multiplied together. So OH negative times the C6H5NH3 positive over our reactant of C6H5NH2. The reason I'm chuckling here is I think I started this lesson being like, oh, it's kind of a short one today. We're like half an hour into the video already. Holy smokes. Anyway, throw these numbers in here. 4.6 or 7.863 times 10 to the negative 6 multiplied by itself again. I'm going to be lazy, just same thing again. Divided by 0.05366752. Green's not looking so nice on that one, but we'll wrap this up here. KB equals, I get a final number here. All right, KB equals, there it is. Okay, so to 2 sig digs, because once again, the pH rule there, 2 sig digs, I'm getting 4.3 times 10 to the negative 10. Woo, that was a lot of work. My goodness. But that actually takes us to the end of the lesson today. So, long story short here, if we want to find our KB value, it's the same kind of thing as what we did when we were finding Ka. Start with your balanced equilibrium reaction, build yourself an ice table, fill that thing out. If you have a pH and you're looking for an OH concentration, remember pH and pOH need to be changed. So you get your pOH to find your OH concentration and then go from there. Really, your goal is get that ice table filled out. You care only really about your equilibrium stuff because that goes into the KB expression just like earlier in the unit when we were calculating Kc. These are all the exact same thing. It all works the exact same way. Anyway, long story short, you need to get some practice at this. Those are the questions I want you working on. I will help you when I get back. Best of luck. Use each other as a resource. And yeah, I'll help you when I get back. See ya.